Okay. Then I come here. Because you talk first.
Panels are very nice.
Huh?
Panels are very nice.
Yeah, they look great.
She's the one who enjoys.
Okay. Maybe check the volume at the beginning when it starts.
I've checked.
It's what?
Why the volume is not?
Because wait.
We don't have volume from.
Yeah, there's no.
The sound button.
Can we ask for the technical assistance?
Joe, where's the audio?
Otherwise.
No. Oh, yeah. Yeah, no, I found it.
But it should be quiet. Turn it down, yeah. It's okay. Maybe you can just. You're good.
I'm going to control it by myself. What?
Two microphones.
So I choose this one because it's lower. There. Good afternoon, ladies and gentlemen. We are Team Nomad from Seoul Studio. We are exploring adaptive mobile system and looking for their potential for self-assembling and deployment. Our design proposal is a behavioral triggered assembly system, marks a shift from architecture as finite, but instead proposing autonomous, continuously evolving, real-time solutions to adapt dynamically to the demands of our environment, constantly restructuring and reinventing itself. So for the Nomad team, we're gonna do a self-introduction. This is Paul Butt, this is Dimitro, and this is Flavia, and me, Aris. Right. Okay, it's really fancy. Okay, the key qualities we are looking for in our system is a system that behaves non-finite, mobile, self-structuring, self-awareness, and then in the end, we're looking for the space negotiating. The Nomad operates on 3 scales of behavioral complexity. So each scale autonomously self-assembling to the next higher order of intelligence and autonomy. The first one is a structural single unit, and next one we're moving to the mobility scale, starting point of collective intelligence of the system. It's an ecology of simple body plans with high mobile qualities for locomotion and assembly. So, and in the end, we go to the spatial configurations with high population of bodies, where parts of the system are locking mobile qualities used for optimization and adaptation through reconfiguration. For the single unit, we explored ways of how a single module can be enabled to have behavior and autonomy. Looked at transformational geometry, and the Buckminster follows the principles of synergetics and the theory of polyhedral systems in transformation. Due to the space packing, self-structuring, and kinetic requirements of our design proposal, we anchor in the world of polyhedral and transformational geometry. The unit is a main building block based on a simple rotational movement of the faces of an octahedron around the vertices of its neighbor. Within this transformation, the unit starts from octahedral state, expands to an exohedron and a cubitohedron, and back to exohedron and octahedron again. Within this transformation, the unit expands to up to 1.5 times bigger in size and changes both orientation and the location of all its faces. This is an analysis of the movement, shows that a series of different relational changes within one unit, from a linear translating of opposing faces to relocation and rotation of diagonal faces. The changes the unit potential search space to aggregate, allowing new connections, a local transformational reconfiguring or other connected structures. We explored different ways of actuating our unit and enable it to act autonomously, from introduction to flexible unit to unit interfaces to internal mechanics and controls. Like this is linear actuators for one unit. And then this is the servos, which can achieve this kind of movement of jumping, running. And then this is a huge walker, use linear actuator again for the actuation.
So our main unit has several design features that enables it to act autonomously and perform in a plug-and-play manner. The outer shell is responsible for the unit-to-unit interface, enabling features like interlocking, connecting and disconnecting, communication, and body plan awareness. Also, our internal mechanism is relied in the rotational movement that describes two arcs in opposing directions. And also where is the core of our unit, where is located the center of gravity. A single unit can be fabricated with simple do-it-yourself components, and all parts except the electronics can be printed in 12 hours and assembled with 2 hours with any desktop 3D printer. Sorry. Looking for a plug-and-play mechanism to connect multiple units, we introduced a positive-negative topography that is applied to all of the faces and avoid the shearing of the units and makes the connections stronger. In order to establish ways of communicating, we created a framework for simulations and prototypes to work together. So we enable this connection from physical to digital world, and we can understand the self-awareness of one unit, where each unit is capable of recognizing their own body plan and the position and state of their neighbors as well. And by this awareness is enabled by face-to-face connections, where all of the communication strategies are placed. Talking about mobility, to simulate a more automated, goal-oriented movement sequence and communication between multiple bodies, we developed a computational communication model that is based on the CA logics, where each unit takes its own decision based on their neighbor's behavior. So in this case, they know if they can open or close, or how they should react according to whatever their neighbors are doing. The signal is passed from unit to unit and determines their behavior that triggers a chain reaction of relational movement. Different sets of behavior trigger different choreographies to achieve directional movement. So here we have an example of how different sets of sequence creates different movements and different sequence of movements, also related to the goal of each unit.
Our initial simulations regarding mobility were exploring how different combinations and aggregations of units behave differently than alone, and how multiple units can take collective decisions following simple behavioral tasks such as goal finding, finding each other, etc., and how the flexibility and range of movements increases with the complexity of the body plan. So the idea of body plans is basically pre-structured organizations that can be categorized and cataloged in an ecology of machines, each showing creature-like characteristics and highly specific behaviors. Their behavior is defined by position, connection, and amount of active and passive units together, where the active unit is restructuring the body, while the passive units act only as passive connections within the system. Within one identical physical body plan, different sequences of activations also define different sets of behaviors, allowing the same physical body to perform various actions and features for movement and assembly. There's, for example, locomotion, rotation, lifting, and expanding of the physical body. Each creature hereby creates its own specific grid based on its sequence of movement and based on its body. And the structure that a creature can deploy is based on the paths that it operates on, meaning when multiple creatures coming together and combining into a so-called super body with decreased mobility, but a higher degree and quality of options and decisions in the assembly process. From this connection of multiple mobile scale creatures, we come to assembly, where in the process of assembly, a highly flexible linear one-day array of units can form two-dimensional grids just by folding and then interlock in a three-dimensional and stable space frame, meaning a highly flexible linear arm within a system does not necessarily remain an arm, but can restructure itself to be a packed volume.
The choreography of movements, the main driver of the assembly process. The movement can be not synchronized, but one after the other, with current being transported over the field and sharing one sequenced energy. Due to the limited lifting capabilities of our single unit that was based on our physical experiments of maximum cantilevering, the build-up sequence are relying on choreographed local movements, resulting in a global build-up. All these simulations are built on a cantilever of 4 units, meaning that there is a ratio of 1/4 of the system being made out of active units and the rest being passive. And these active units are located in the anchors and branching points of our structure. The system used 2 different modes of activation, which is the active and passive, and reconfiguration and assembling with a grid. Using its transformational abilities to move units through the grid as local intervention, for example, reinforcement, the existing structure is used as a climbing frame, where passive units are lifted and passed through the grid. The second sequence of assembly is based on active body plans that deploy themselves along the structures, climbing horizontally and vertically, and also being able of reconfiguring their body plans. The abilities of the system to transport itself and build up is relying on its ability to attach and disattach from a cluster and the idea of transporting material through building blocks.
Different growth and branching logics adapted to fit our geometric criteria. Regular structural grid has even number of elements in a row, providing different criteria of porosity and volume packing. The nomadic system originates in several seeding points, then it reaches for the points of stability, bridging, and it finds a touching and anchoring point on the ground. It has ability of live reconfiguration during the building process. Special rigidity is achieved by building up trusses in the places we need it. The maximum cantilevering number of elements is received from the physical experiments, which is 6. Extension function is the free arm, which help us to combine the structure with another structure into the overall shape. a system is given the same task building vertically under different circumstances, such as available number of units, distribution of seeding points, and construction time. Construction time is the proportion between construction time and number of units is exponential. So the more units we have, the more time we consume to build it squared. Bridging between specially divided seeding points is being built using wide base, and the structure stabilizes itself and then cantilevering. The system can have multiple seeding points, which can organize in several structures, several grids, which weave between one another, reinforcing the overall structure within a human scale. The adaptation to changing goals or conditions is provided by recalculating possibilities to build and connect. It takes decision of deconstruction and redeployment. Within a certain period of time, say 32 hours, the system rebuilds itself, building human scale elements, regular structural elements such as vertical columns and others. And the number of units involved into this reconfiguration is roughly 10,000 units. It can be used totally or partially. At the same time, the system is trying to calculate structural stability. It reaches the point of structural stability in within a goal to find connection and to connect with neighboring elements into rigid structural shape. These rules of logics of deployment result in a diverse variety of structures with different special qualities and potential urban scenarios.
So when we are looking at the full building life cycle, you can observe the various building strategies and capabilities of the system as they translate from one scale to another, and how it is capable to adapt and react on each of them, starting from horizontal organization on the ground to build up a base for then vertical deployments where material itself is actively climbing and being deposited horizontally and vertically through an existing structures, units negotiating with already nearby built structures, deploying new scaffolds along or next to them, from where they can reconfigure without the need of additional new units entering the system, but just the repositioning of configurations. An urban scenario, the system is adapting to changing needs and scenarios of deployment during the path of a day, units entering and leaving the building sites on demand and migrating where they are individually needed for build-up sequences. And out to a bigger, from the local or park scale to a bigger urban scale, where a global organization of the system is deploying or migrating from different sites, going on site-specific scenarios and locations within the scale of a neighborhood. And Nomad creates a living cycle of endless evolving scenarios or possibilities of urban deployment. And within this, we imagine Nomad to be a part of the city and being integrated into its daily life as an infrastructure that's responding to us on multiple urban scales. Thank you.
So these first ones here were our first explorations in terms of geometry transformation and packing logics. Also, we start to explore like the connection of faces and the face topography and how they could connect and disconnect and be part of the system. We also explored the ability of single units to move, to have mobility qualities. So we explored soft faces and soft units and how they could deform and transform. Those set of models are the first explorations in terms of actuation, so how we could make these units to open and the relation of the faces, how they could affect the center of gravity. Here is our most recent prototype with the designed joints and the center of rotation where we have the wheels and the servos that connects the opening and closing of the system. This is one example of our walker structure. It was an older prototype. This one is the most recent one, but we only explored the opposing face connections here, so we expand and close, but we couldn't achieve full complete movement. Here is the sets of iterations of our face topography and how they could connect and disconnect, and how strong is the connection between one and the other. And play with it. These one are all of our, it's the 3 scales of our system. We have the unit, we have the medium aggregations and the high populations. Here is a urban scenario, proposal of urban scenario, and the life cycle of the structures being built and the walkers coming into the structure and building themselves. Here was our models for exploring space packing and how we could fold one string of units and fold them into 3D geometries. And here is our attempt to create the possibilities of a 1-to-1 scale model where one unit transports passive material through the structure. Thank you.
Thank you for that. I really like the prototypes you've done. There's some exceptional work in there, and the tessellating patterns. One of the things I wish you'd shown a little bit more on with regards to those is when you were talking about the limitations in terms of what they can lift and what they can move. And I'd like to have seen what you actually tested and how you pushed that through. I'm sure you did do, because it all seems reasonable, but just to show the working behind that, whether there's opportunity to expand on that and how that could be done in the future as the magnets get more powerful, the motors get more powerful, or whatever is your limiting factor. And I really love the image of them running through the street to a square to join the people and respond to the people's needs. But I was wondering if you could talk a bit more about their interaction with the general population and how you see, whether you see this as a aesthetic thing that just creates a different environment, or whether you see this as creating furniture, and whether it actually responds to what people are doing, or whether it's got a pre-programmed movement, or how you see that working.
We are thinking of bottom-down organizations or logics of the system that come from the unit, so no superimposed master plan or any or built by order decisions from top down. We don't think of the system as reacting one-to-one to human, but more following general available urban data or open feeds that could motivate their handling.
And so does it have data gathering capabilities, or so with data gathering capabilities and responding to that, or?
Well, the unit has a sensory system, as in it can locate other units that are around, or it is aware of not only face-to-face neighbors, but up to a certain degree has an organizational cloud brain of being aware of the rest of the system together, or to know where to build and making decisions of a global system and not alone.
Can I just ask sort of how far you've taken that notion of self-awareness, for example? You showed an array of a very, very large number of these cells at one point. You've actually done a computer simulation of how they would manage to be self-aware of themselves over such an array and how they might communicate. I mean, I'm not taking away anything from what you've done, which I think is fabulous. I'm just wondering just how far you've taken it and where the kind of limits of this exploration lie.
The last computer simulations of the you see are based on somewhat of a branching awareness where we put in the limitations so that it cannot do physical experiments, how much it can connect, how much it can lift, how far it can go, and then it's.
But also the first experiments we did using the CA logics where we could input some constraints that were more close to our system in a sense like how many faces could be connected because not all of them can have connections, and also how many in the array could it respond to.
How many connections can it have before it interlocks in a high amount of units and constraints such as.
For example, I think you just said it was a cellular automata-like kind of configuration. I mean, does the whole thing update simultaneously on the tick of a clock synchronously, or is it able to explore asynchronously, parts of the structure responding at a different time to others? In which case, you know, how do they make sure it lands and so on? Otherwise, I'm just wondering how slow it would be in real time with that number of units each trying to negotiate socially with another 10,000 units as to how to deploy themselves.
In the latest simulations of build-ups, we have the limitation that only the outer layer can reconfigure or adapt, basically, while there's parts of the system that lock in or are packed in. Only the outer part of the structure can.
The system cannot reconfigure from the middle. It can reconfigure only the outer level, so it's step by step. It's quite a sequential process. It's not like 10,000 units are reconfiguring simultaneously.
By necessity, it has to continuously partition itself. So it builds up different ordering principles because they are already, instead of an individual unit behaving always as an individual unit, they start to accumulate with particular behaviors and body plans. It's kind of building on the things that you were working on things that Carl Sims was working on, evolving body plans that have the capacity to actually partition this. So the population governance is not relegated to one, but it's aware of a partitioning between each individual thing. So for example, the holistic body of a unit is broken down to face-to-face relationships, and that sort of maintains an integrity for it to understand where it is relative to these larger organizations. And that has very practical facility, which is basically understanding, as much as it's building something in the context of dynamics of people and occupancy and all these things, it's also breaking things down and taking decisions in terms of where they would migrate and relocate. So it's not a generic CA that just gets deployed and the system continuously recalculates. It has to build higher order learning, and the capacity to do that is relegated by the way that it actually tries to understand itself. So choreography is just as much a determinant of that kind of body plan recognition, because as soon as this loses its individual unit component and it becomes a segmented body, now its movement behaviors are predicated on its own body plan.
So if the body plan was to have two hands and they're negotiating separately, you could finish up with the two hands different? Yes, right.
I'm fascinated by these questions because I'm also puzzling about that. I don't think there's been answers thought through and worked out, I think. And I was wondering about the concept of self-awareness in the earlier project. Obviously in the CA you don't have self-awareness in the sense of, or it's awareness beyond an emergent pattern. It's just coming out of very, very local responses and which are proliferating. And I think and a lot of the configurations which are happening, including the body plans, are in fact authored, obviously, by you guys. And so I think it's, for me, it's an interesting question. When I see the this leads me to a suggestion. And I see these configurations you're generating here, which you have authored, clearly. And they have this kind of crystalline condition. And I feel that needs to be challenged in this discussion. I would say it would make more contemporary the whole project if you had, for instance, the kind of structure that Philip Locke investigating. Let's say you're talking about compression shells, but the innovation here is that we're now able to have these with less symmetry. The classical version and the invented version is always a perfectly symmetrical one, equal grid, and now we can start to grapple with irregular conditions. So the side conditions is irregular. Something builds up across and picks up contingency of side, of asymmetries of side and use, and now you agglomerate some kind of based on local rules, which is partly more random. And then the question is, what is in fact noticed? And what I see potentially here is perhaps a stress sensor or pressure sensor in this, which then could lead to some kind of guidance of the further process, or in a kind of topology optimization and erosion back of processes. So I think we would not be in the world of these kind of regular lattices. We would be in a world of more random looking, which is then kind of self-eroding or through some feedback which needs to be named. Not just some kind of claim for self-awareness, or awareness of what, at what points, with what consequences. So I think it's a very important discussion for this. The other point I was wondering about, I love the thinking in terms of these body plans, these molecules which come out of these, and the way you've investigated them, and they're really striking, inspired by Carl Simpson and others. Of course, these molecules, these body plans, are all based on an array of atoms. And I like it when you show it here that they light up, the red pieces become the active pieces. But that needs to be clarified to me. Is it the active passive is always only a potential? They're all in fact identical, I suspect, which means somehow that the body plan condition you generate is just in your mind, that that's the way you want to think through what the thing is doing. Wonder how the system itself would maintain body plan consistency, and how is that actually embodied as a relatively stable reproduction. But at the same time, at a certain point, you want mutations, and the body plan dissolves. But for me, the body plan is an intellectual construct, which I really find it fascinating. But I wonder how the system actually knows about bodies and body plans. And one way perhaps to do is you need to put constraints. Basically, the body plan trajectory is just a subset of the universe of possibilities, and the constraints might be actually through reducing capacity. If you actually, deactivate and lock out activation out of a certain pieces, then maybe then the universe of possibilities of the molecules aggregating into gets kind of body plan likeness. At the same time, the power is beautiful, where you show that something becomes a finger thing, becomes a full dome, so of course, since it's a voxel, it is totally unconstrained as a possibility, and yet we want the body plan concept, but the body plan concept is only at the moment authored by you as an intellectual reference, and I wonder how the system partitions itself into these semi-stable body plans.
I wasn't going to let you get away with that. No, they're going to answer. This is between us now. I mean, I think that there's something that needs to be understood when we sort of try to make a claim for an articulation of a system, because you're saying they're authoring that. And that is a little bit suspicious for me, because it implies that somehow it's a willful projection. But actually, it's a recognition of these transformations and those constraints, and then you take a goal like mobility, and that informs what they're calling a walker. When you mention this relative to Philip, I'm just going to let you know it's just different. What you're doing is different. It's like basically asking every one of your bricks how its neighboring brick wants to be, but actually allowing it to talk back to you and basically argue back that decision. So this isn't a project about form, this is a project about continual reformation. And I think, of course, it's clear that it should develop goals and it should do all of these things, but let's talk about the status quo of where this is at the moment. People talking about self-assembly. Some people have gotten to the point where they can use some multi-materials and make a cube. These kids are deploying, and I'm talking about very so-called intellectual, high-level technology institutes in the States. Here these guys are trying to speculate about what it is actually doing. And they're trying to demonstrate some capacity to do that. And where this is relative to, I think is not at just the level that this is becoming a creature like Carl Sims, because Carl Sims basically assumed because it looks like a creature, it is a creature. And talking about it in the 90s in a virtual world is radically different than trying to make it a piece of tangible media. As crude as they are, at the same time, they are very articulate in some sense. And for me, it's an acknowledgement that the passive element and the active element could be the same, or they could be different. And I think the fact that these things start to use each other as infrastructures for creating space gives me a lot of belief in their capacity to think through this. So the argument about symmetry or asymmetry, for me, is not really an argument. Only because of the fact that at the lower resolution, of course, it's like a voxel, but making the voxel mean something and then allowing the organizations, which is the part of the project that hasn't been really fully vested. And I think that's where I would sort of say is really where the project should really start to evaluate what is it really trying to take out of its context, what context really means. It's not about sight, it's not just relationships to other elements. The idea of some of these things having a stimulus for play or for structuring or for other capacities, I think has to be understood. Like one scenario when it starts to become illumination becomes really interesting if you really do see this as an urban project, which is a claim. At the moment, it's not at that level, but if it was, what is that kind of fitness criteria? If it is illumination, then that becomes a different sort of driver for distribution. That's not relative to geometry, it's relative to some other factor. I only mentioned...
It was much more... my comment was far less critical than your answer implied, by the way. It was 100% within that word, and fantastic research. I was trying to understand, in the swarm of the units, the decomposition into body plans, which is a fascinating idea. That element, and I like the fact that it is not an absolute, that it is a temporary, sort of semi-stable, that my arm is not always on me, but it could maybe migrate onto Pierre and there. That's in that world. But yet you want to talk about arms and legs and crutches and that was my question. How is that? At the moment, you make these decisions and set up, and then you say, now I'm deciding to switch from one to the other. So I was wondering, in terms of self-awareness, conception, etc., to what extent becomes that an opportunity and decision of the system? And that means it must be some kind of evolutionary process. That's why I like the Carl Sims reference. This kind of, because that's the degree of freedom. That's the thing where, I mean, the units will always be the same, but what changes is, I think, the body plan decomposition and the behaviors which go along with that. Yeah.
I mean, one thought, one thing to consider in a way would be that there's a profound difference between a simulation space, which is where the project currently exists. There's an amazing perfection to the simulation. Everything matches up. Everything aligns. And it's curious in a way now that you are in fact proposing this goes out into the material world, which nothing lines up. There's wind, right? There's asymmetries, and I'm curious about the capacity for the system to really, for a bottom-up system, to really deal with that in the way that you're asking these joints to begin to meet up across 10, 20 feet. And how would it begin to sort of do that in a kind of really practical way if it wasn't self-aware and if it wasn't able to have, let's just say, kind of a heuristic component to the system where it might have some self-awareness, and so there's a kind of funny thing because we're dealing in a world that doesn't align in the way that you might need it to align in order for these kinds of systems to sort of work. And another thought is, it seems to me that there would be a real difference between, like, this is the drawing, when these guys are the crawlers, right? There's a kind of for me, a different computational drive. It's a high level computation at that point, where you would need things like edge detection, and you would need a lot of intelligence, perhaps at the level of the single cell, but really you would need those cells to be highly, highly coordinated. It wouldn't be a slow movement, it'd be a fast, active, self-aware, context-aware unit. And the way it would actually operate is it would need to learn. Its first few steps might be clumsy. In fact, it would fall over like a child, right? But as it began to understand its environment and would begin to input variables, and it might sprint like a cheetah, right? It might be able to just really move. But could it evolve quickly in order to do that? And does it also have to relearn those steps, right, every time? Because in a lot of ways, this is what you're sort of saying, that they're low level. They have very little memory, they have very little capacity. So they would literally need to evolve rapidly every time that they want to self-assemble to scurry across Bedford Square, right? So that's another thought, is how do you begin to input, human level or animal level or creature level intelligence into these things? And I'm not sure you can do that unless they have the capacity to learn and to really evolve. And so they might not be as low level, really, as you actually think. The sort of third thought I had is unit evolution. For me, that would be an intriguing idea where they're not equal, let's say, okay? They might start out equal, but over the course of an evening, they might evolve certain mutations that would allow them to kind of optimize, so that at the end of the day, they're actually all slightly perhaps different. Maybe they've got some kind of capacity to shift themselves, become more flexible, more pliable. Some might be more rigid, some might be more flexible. By the end of the cycle, they're highly evolved and kind of highly unique. And I think there would be an incredible advantage for a system like this. And so, yeah, these are things to consider, I suppose, in the next phase.
I just want to pick up on a lot of the questions started with global and local evaluation and what types of rules and bottom-up rules, the question of the body plan. I think all these questions are very informed questions. Like, the jury understands quite well and has a lot of experience in this in general, as far as architects go anyway. But if we were to consider this a regular building, often one wants to do a global evaluation. And I think this type of territory, as Theo mentioned before, it's not really about form, it's about a constant assembly and disassembly. It's a constant process of building and unbuilding. And we're dealing with a terrain that things like global evaluation are difficult, as some people have hinted on. In the physical world, in the situated world of this, it's very difficult. And if you have a goal-orientated task, normally in a simulation environment, you are trying to do a global evaluation of that, right? Like if it's a structural thing or, say, a CFD analysis. In this particular case, something like structure in the situated world can be evaluated at an individual level. Am I under enough stress or too much stress or anything like that? So suddenly something that in a simulation can go between global and local evaluation could just be treated at a local level. But in terms of design goal, that's where I think it gets interesting. And that's where we can only start to speculate and open up what can be there, because to have a global evaluation in the situated world of a design goal, I'm not saying it's impossible, it probably is very possible, but it's certainly very difficult. In the sense that it means that all these elements actually all do really have to communicate together. The body plan's an interesting one because what it allows you to do is enable a certain local level of evaluation and also be able to inbuild from the bottom up a series of design effects from certain designed relationships that, you know, conditional statements, for instance, or conditions that could be met, event-driven rules that could guarantee you certain things. So I actually think the body plan's an interesting one because if it was completely bottom-up, we would have no authorship. If it was totally top-down, we would have difficulties with global evaluation. But to go with the body plan approach, then you can start to almost predict certain types of things that can emerge, but there's also the possibility for adaptation or to different site contexts. So I think that's a good thing. And then I would say to keep Jason's comments on board, that those body plans could evolve, or Patrick's as well, that they could, you know, evolve over time. You could be looking at people like Hod Libson, who actually does try to locally, from a bottom-up perspective, define or understand what the body is of something once it's assembled. So perhaps, you know, you have a series of conditional rules that allow the body plan to be flexible, and the cells have to work out how many they're connected to and what is actually their body at any one time. But I think it's really good work.
Yeah, I'd like to continue on that. I think in terms of the behavior, it would be useful to actually connect that directly to the physicality. I'm thinking specifically in the context of power density of the motors. So in order to determine the size these would actually be, we might want to look not just at the available motors, which in this case are servos, so they're built from the servo outwards, but a sort of precursor to the research where you look at what motors can we choose for optimum speed and optimum torque, and therefore different types of activities they might undertake. So we might find that the size that's chosen, that's now in all the simulations, is not the optimum size. It might be better to have something much, much bigger than that, with a much more efficient motor that can travel across town, build something quickly, and then wait for motors, some of these units with motors that have the torque capable of building these structures, and capable of maintaining the levels of accuracy that are required. So it would be useful, I think, to build around those ideas. There are current robotics, sort of industrial robots that are capable of lifting their own weight, and at a certain size that would be completely impossible, so very large ones couldn't do that. The small ones become very inaccurate with sort of bendy servos and things, so there is some sort of optimum that could be investigated there to help push this into something that might be realized.
So, picking up on the motor, actually would be amazing to see them running here, for me, personally speaking. Also, the level of graphics was really impressive, guys, really nice movies and stuff. And you though left me with a kind of ambivalent feeling to it, because in the graphics, as soon as people appear, they start first, they are hunted down by, it feels like a little bit, and at the end that there were spectators. Sorry, yeah. And I really wish, and I think we should talk about functionality, right? And if this reassembly is a functionality, it's one. I think there's many more that should come afterwards, and I would really hope in the next phase that you turn the human being from a spectator to a user, to an active user of that, therefore loading up this with different functionalities yet to be kind of defined. And I think then, this would be really interesting, and hope to see more of that then.
I will pick up on this one. Because I think that everything about behavior has already been said and is absolutely wonderful how you have presented it. Maybe what I would like to add is that in relation to this continual reformation of matter that Theo was speaking about, and the comment on functionality, that really these units have the possibility to stay half open. And I really, this is to me the most beautiful moment almost in the space in between, so that there could be more than generating structures per se and building up things and unbuilding and building, but also to be temporary scaffolds, for example, for directing air, or to create permeable, porous kind of structures that could begin to move and almost reconfigure flow or things like this because of this behavior. So where really the large structure is beginning to do something because of the possibility of these intermediate movements. I would really like to see that if it were to continue.
This may be another thought that I've had recently. I'm thinking about the fascination we have with low-level, bottom-up systems that are operating off of very simple rules. And you know, I feel a little bit like right now already we have the ability to embed high-level computation on the tip of our fingernail, and even smaller, right? And I'm curious, Theo, in terms of in the overall thinking, what actually happens when we have high-level computation, you know, in literally these little devices, right? Their capacity to compute and be self-aware sort of changes the domain a little bit, or let's say we're looking at low-level systems like ants, right, who don't have that computational power, and so let's say their effectiveness as a model may be limited, and we don't really somehow have a model for a superorganism made up of highly intelligent pieces, and so that's in a way where I wonder whether biology has maybe hit its limit for us as a kind of thing to study. Like, what do we actually look at when we're creating, you know, super intelligent things already, right? So it's a larger question for everyone, I suppose.
I mean, just like I probably would like to disagree a little bit on like how we're assuming that we have like so much computation power to put at our fingertips, but if you actually think of currently which system has learned to walk, like whether it's like the Boston Dynamics thing or the Stanford robots, or like, I mean, the amazing amount of computing power needed is still not at our fingertips. So I think that the sensibility that like it started at behavior and what behavior could lead to, and then Patrick kind of suggested how did the system become aware of its limbs, and then it suddenly became like how will it learn to walk. I think we're kind of running a bit further ahead of like what technology is currently capable of.
This isn't architecture responding to current technology and finding somehow how to apply it to architecture. Like I'm going to be slightly animated because I love both of you, but I kind of want to say, like, in a collegiate way, just because it's recorded and for all the people. No, but I mean, like, this isn't a response that there's a technology and we're going to appropriate it into architecture. This is, and to answer Jason's comment, it's not that this stuff should be low level and stay low level. Of course, we're trying to find ways to machine learn. Even speech to text needs a learning kind of thing, just to take something and make it something else. And of course, there's an acknowledgement that we are really at the infancy of this. I think if there is an agenda, which I think there is, it's about architecture participating with this. Because if all devices have some form of embedded information, and materials have a different form of embedded information, and of course I see this kind of stuff evolving beyond the mechanical, but I think these prototypes shouldn't be thought about like literally this is going to be outside, but this is a way for them to actually understand the complexity at hand. So in some projects, you know, like the previous one in my studio, we ran a little far with the space making because at some point everybody wants to be an architect and make space. But at the same time, I think it's necessary to make a couple of leaps beyond what it is, because Hod Lipson made a lot of progress, and of course this studio is based on it. So his 15 years worth of research enables it. But at the same time, we went and we visited his lab, and we saw where they got to, and we saw because people don't see interest in it, that research is basically being shut down. And to be honest with you, this kind of speculation, I think, helps just raise the research level above. And that's the only reason why I'm sort of also going to jump in on the, because some people will look at this and say it's tech, you're grabbing tech, servos are cheap, so now this enters into the architectural domain. We see a house that's completely reconfigured, restructured. We see components that are doing that. I think that there is a continuity of the language and the discourse that are much more symbiotic than appearances may be. So because it has geometry from a component perspective, doesn't mean it's a component project. This isn't a grasshopper population of stuff on the surface. And so at some moment, it has to sort of state its own terms and also the working methodologies, which are not necessarily always clear. So I just say that because of the tech stuff, Sanjay, because
no, I was, again, like I wasn't trying to be critical. I was just trying to say that there's like a lot of interesting things that they did, and part of like unlocking.
I'm not talking about what they did. I'm talking just the general blanket statement, right? Like the Internet of Things, all of these other things are starting to actually look in between the things themselves. And I think this is really important for the next 3 years of what we're going to be doing, that it has to go beyond what we see in front of us if we are going to speculate. And there's a necessity to do that. It's just like, that's not even an option from my side, just so everybody knows. It's necessary. It's the only thing that potentially we can really, at a very high level, contribute to these conversations. If we're talking at the level of Google and stuff like that, they can mine space. Now they're trying to do something with it, but they do it through appropriation. So Boston Dynamics gets pulled into the conversation, so does other people. But at the same time, we're talking about a bigger problem, right? Which is going to be constructing new spaces, environments, infrastructures for all of this. There is no solution space yet.
White flag.
Sorry?
White flag.
Not white flag, I'm just saying. Like, this is why we do this. This is why this conversation is open. This is why it's going to continue with the next project.
No, I mean, I want to speak to the project because I think it's perhaps answers a lot of the questions that were opened up by the previous one from your group, Theo, and in the sense that the DRL in general is passing on knowledge. I think this one is an incredibly generous project in that it contributes a lot of solutions to the geometric questions of how these things could happen. And this kind of provisional body plan, I think, is a major contribution within that dialogue. So because of that, since you've gone so far into kind of questioning all these things, then I'm really interested in this kind of dialogue between top-down and bottom-up of what could be the kinds of motivations here and how they would be situated and how they might be able to play out. And I think, for example, like you talk about the rules being somewhat like CA, it was very useful that Game of Life had a story behind its rules. We didn't just have to remember that 3 meant this and 4 meant that. We had this story about being overcrowded or being lonely and this sort of thing. And I think it could be quite interesting for you to try to attach potential motivations as thought experiments to be like, hey, I'm the little guy who just loves to be as high as possible. And no matter what I find, I'm going to climb and get to the top. And if they were all like that, it would be this very weird game of the dudes pushing each other down to get to the top. or someone else gets hacked and it's now I'm the chisel of society and I just try to hack away at the bottom of anything that looks like there's a lot of load, and so starts creating massive catastrophe collapses or all these kinds of things. Like, I'm curious, of course we have kind of these limited low-level rules, but you could have really big outcomes with certain characterizations of what they want to be, right? Like the Swiss one might come along and anything that's not square enough, it will put itself there and get in a really straight line, right? Or the Gothicists are really, wherever there's an arch-like thing, it's like, I'm going to fill in the dot that makes it more like an arch. So I'm curious about you making stories to add on top of the incredible technical and geometric sophistication.